Hello everyone, I'm Amaury Bouchra-Pilet and I'm going to present you the work I did with Dr. David Effray and Professor François Teyani on OCRE, Agent Utility Centered Clustering for Cooperation Recommendation. So what is the problem we want to solve? We want to provide recommendation to rational economic agents for cooperation. In the setup we consider, agents can have different expectations, and cooperation is better if people cooperating have more similar expectations. In general, we also consider that cooperation would be better if more people are cooperating. But there may also be cases where this is not the case, where a too large group just does not work well, and we want to be able to cover such cases. And we also want agents to be able to work alone if the cooperation is not a good option for them. What is the approach we propose? So, we project agents in a world space representing their expectations. We have an utility function based on the number of cooperators and the distance of an agent to the barycenter of its group to measure the interest of the agent for the proposed collaboration. Finally, we use a local optimization-based clustering algorithm based on k-means to provide cooperation recommendation. Here is our utility function. As you can see, the utility of an agent A for the group G is equal to the product of the distance from this agent to the barycenter of the group modified by a certain normalization factor and the size of the group with a certain utility factor depending on the size. So in the general situation we would have this to be an increasing function, but we may also, in situations where too large groups are not wanted, have a function that stops at some maximum or even decrease if the group becomes too large. And our objective is to maximize the sum of the utility of agents while preventing individual insatisfaction. So insatisfaction is a situation where an agent is with our algorithm associated to a group but would prefer to be alone or would prefer to be in another group. Here is our clustering algorithm. So here is the initialization phase of clusters. So it's based on k-means. So we consider the number of clusters wanted to be a non-parameter. We can actually search for that parameter using some other algorithm. This is what we did in our experiment. So to initialize this algorithm, we need to just put some random cluster centers, k random cluster centers in the space, and we try to have them distributed rather evenly in the whole space. And here we perform our optimization. So for k-means, the idea was to simply at each step add agents to groups based on the distance to the barycenter, only the distance to the barycenter. And for our algorithm, what we do is we use a double loop instead of k-means, we choose one. And for all agents, we will perform two phases of optimization. So let's look at this inner loop first. In this inner loop, we will consider the barycenter of the groups to be a given parameter, and what will change is the estimated size of the groups. So agents are added to groups based on their fixed barycenter and the actual size in the optimization process. And we iterate until no agent wants to change groups, the size are fixed. And after that inner loop, we update the barycenters. And then we continue doing this loop again and again until all agents stay in the same groups after this loop. So this process is actually not guaranteed to converge. Because of the combination of the effect of size and distance to barycenter, we can prove that this algorithm does not always converge. So to solve this problem, of non-guaranteed convergent, we decided to create a guaranteed convergent variant of our algorithm. So we removed the lines in red and added those lines in blue. So the difference between those two variants is that in the classical variant, both loops are guarded by a line where essentially no change is the condition. But we cannot guarantee that no change will ever happen. So what we do is that we use metrics that would always move in one direction, and we stop when those metrics don't move in this direction. So here we use the size of clusters, here we use the sum of utilities. And this way we can guarantee that our algorithm will converge. But the main issue, it comes at the cost of not guaranteeing that everyone is always in a group that will satisfy him better than all other groups. We prove in our experiments that this is a very limited inconvenience, but this will happen, and this is actually something that we can't prevent because it's actually just impossible to provide a solution that to this problem in the general case. In the general case, we can't guarantee that there exists a solution where all agents are satisfied and do not want to change. So, in our theoretical analysis, we essentially proved two things. The red variant of our algorithm always output a Nash equilibrium, so a situation in which no agent want to change groups. And the blue variant always converges. Let's talk about our experiments. So, the competitors: k-means, the classical clustering algorithm which we used as a base for OC, and optics, which is a well-known density-based clustering algorithm. The dataset we used: first we used synthetic data. We actually generated this data using Gaussian distributions, and we mixed several Gaussian distributions to create data with clusters. And we also have two real-world datasets. So BuddyMove is a dataset where you get notations from people on holiday destinations, and Wholesale is a dataset where you have the annual spending of different buyers on different type of goods. As a result, we obtained unsynthetic data. So what we see here is that in this situation where you have a center with high density and outskirts with low density, our algorithm is able to identify this high density center, k-means and optics are not. In this situation where you have three closed Gaussians, our algorithm identifies them perfectly, k-means also, optics do not find anything. And in this variant, the Gaussian star, so we have one big Gaussian in the center and four smaller Gaussians, then neither k-means nor optics can find anything. But our algorithm manages to identify those Gaussians perfectly. And what we see is that it's not really obvious to identify them, but we can. Here are the metrics we obtained on utility. So, here are the agent losses in terms of utility, and we can see that our algorithm is much lower than k-means and optics when it comes to agent losses. Also, when it comes to the share of agents with losses, only 1% of agents are unsatisfied by the solution proposed by our algorithm, compared to 8 to 7% for k-means and optics. And the global utility has shifted, so the sum of utility of all agents is mostly the same for our algorithm, k-means and optics. So let's talk about how we can limit the cluster size. So what we do is that we change the function that gives the value of a group based on its size. So for the classical variant, which we used in the previous experiment, we use a square root. Here we use a square root, but kept at 20. And here we use this more complicated function. Essentially, we grow until 20 like for square root, but after 20, we decrease. And what we see is our algorithms with this utility function is able to change its group allocation to fit the constraint of having smaller groups. So here, with the original variant, only one cluster. Here, with the capped utility, smaller cluster. And here, with decreasing utility with larger groups, even smaller clusters. Here are the results we obtained on our two real-world datasets, BuddyMove and Wholesale. What we see is that Oak is whether able to identify clusters in all situations and also to leave agents alone when they are not in obvious clusters. K-means here is unable in BuddyMove to identify clusters correctly. It's able to find some clusters in Wholesale, but not able to leave people alone. And Optics is not able to find anything in the datasets. And here are the metrics. So for this dataset, there is one additional parameter, which is a scale. So actually in the dataset, you have real values, but to associate these real values with position in the real space we use, actually you are rather free to set the scale, because the real values present in the dataset are not really made to compute utility, so you have to scale them before. The scale is a parameter that is to be chosen by the user of the algorithm. And here we tested different values for the scale, and what we see is that with higher scale values, the agent losses increases dramatically for both K-means and Optics, but not for our algorithm Oak, where the losses remains near zero. And for the global utility, we see that with scale it decreases for all algorithms, slightly more for Oak, but not much more, and we can actually consider that this small loss in terms of utility is an acceptable trade-off for this significant improvement in terms of agent having losses. So this means that with Optics, more than 40% of agents, nearly half of the agents, are actually not satisfied with the affectation, while with our system, no agents nearly are unsatisfied. General analysis of our results: Oak is more efficient than classical clustering algorithm to identify clusters in synthetic data, what we showed in our experiment with Gaussian mixtures. Oak strongly reduces individual losses, as we shown in our metrics. Oak performs fine on real datasets, as we shown in our experiments with BuddyMove and Wholesale. To conclude, we defined a new class of hedonic games for cooperation recommendation. We created a clustering algorithm to solve these games, and our clustering algorithm is better than existing clustering algorithms to solve such games. Potential future works include applied for machine learning, which we did in the extended version of our paper, which is available in the Archive Ouverte HAL. And we could also try to extend this to hierarchical clustering, so in situations where you want to identify clusters with subclusters, we did not try to do that. It would be an interesting extension of our work. Thanks for your attention. Do you have any questions?